This is going to be a series of talk about quantum internet from the perspectives of networkQ, a stealth mode startup focusing on quantum network research, quantum network simulations, and quantum network intelligence switching solutions platform. I'm Shri, the co-founder of networkQ. Let us discuss some basics of quantum internet and move on from there to advanced topics in the upcoming series. So, what's quantum network? In the quantum world, data can be encoded in the state of qubits, which can be created in a quantum devices like a quantum computer or a quantum processor. And the quantum internet, in simple terms, will involve sending qubits across a network of multiple quantum devices that are physically separated. Crucially, all of this would happen in the properties of the unique quantum states. That might sound similar to the classical internet, but sending qubits around the quantum channel rather than a classical one effectively means leveraging the behavior of particles when taken at their small scale, that the quantum states, which is called the quantum states, which have caused a lot of dissatisfaction and dismay among scientists for decades. And the laws of quantum physics, which underpin the way information will be transmitted in the quantum internet, are nothing short of unfamiliar. In fact, they're strange, counterintuitive, and at times even seemingly supernatural. Yeah, I mean supernatural. So that's something which is one of the most important discussion of this series on quantum internet, and how it looks like supernatural. And so to understand how the quantum ecosystem of the classical network and upcoming further network, you might just want to skip certain things of the classical computing, the classical quantum networks, but there are a lot of similarities between classical networks and quantum networks, and we will be discussing that also in the upcoming series. At least the next 1 or 2 decades, we see that a lot of development is going to happen in quantum internet, though it will get stabilized after some point of time. The central of quantum communication is the fact that qubits, which harness the fundamental laws of quantum mechanics, behave very differently to classical bits. As it encodes data, classical bit can effectively only be one of 2 states, just like either off or on. And just like that, a dog has to be either dead or alive, so does a bit have to be either 1 or 0. Not so much with qubits. Instead, qubits are superposed. They can be 0 and 1 simultaneously in a special quantum state that doesn't exist in the classical world. It is a little bit as if you could be sleeping and woke up at the same point of time. The paradox is that the mere act of measuring a qubit means that it is assigned a state. A measured qubit automatically falls from its dual state and is relegated to 0 or 1, just like a classical bit. The whole phenomenon is called superposition and lies at the core of quantum mechanics. Unsurprisingly, qubits cannot be used to send the kind of data we are familiar with, like how do we communicate today on the internet. But the strange behavior of qubits is opening up a huge opportunities in other niche applications like defense. It's very secured, and that's something which is we're attracting a lot of attention from many governments, many countries. One of the most exciting avenues that researchers armed with qubits are exploring is security. When it comes to classical communications, most data is secured by distributing a shared key to the sender and receiver, and then using this common key to encrypt the message. The receiver can then use their key to decode the data at their end. The security of most classical communication today is based on an algorithm for creating keys that is difficult for hackers to break, but not impossible, of course. Hackers are smart. That's why scientists are looking at making this communication process quantum based. The concept is at the core of an emerging field of cybersecurity called QKD, the quantum key distribution. QKD works by having one of the two parties encrypt a piece of classical data by encoding the cryptographic key onto qubits. The sender then transmits those qubits to the other person who measures the qubits in order to obtain the key values. Measuring causes the state of the qubit to collapse, but it is the value that it is read out during the measurement process that is important. The qubit, in a way, is only there to transport the key value. More importantly, QKD means that it is easy to find out whether a third party has eavesdropped on the qubits during the transmission, since the intruder would have caused the key to collapse simply by looking at it. If a hacker looked at the qubits at any point while they were being said, this would automatically change the states of the qubits. A spy would inevitably leave behind a sign of eavesdropping, which is why cryptographers maintain the QKD is probably secure. QKD technology is in its very early stages. The usual way to create QKD at the moment consists of sending qubits in a one-directional way to the receiver through optical fiber cables, but those significantly limit the effectiveness of the protocol. Qubits can easily get lost or scattered in a fiber optic cable, which means the quantum signals are very much error-prone. The struggle to travel long distances. Current experiments, in fact, are limited to a range of hundreds of kilometers or even less. There is another solution, and it is one that underpins the quantum internet to leverage another property of quantum called entanglement to communicate between two devices. I was talking about supernatural, right? Yeah, this entanglement is what is going to cause that supernatural kind of stuff altogether in the quantum internet. When two qubits interact and become entangled, they share particular properties that depend on each other. While the qubits are in an entangled state, any change to one particle in the pair will result in the change to the other, even if they are physically separated, which means they are not physically connected. The state of the first qubit, therefore, can be read by looking at the behavior of its entangled counterpart. That's right. Even Albert Einstein called the whole thing spooky, action at a distance. He was not able to accept this theory at all because you see it is not connected. How can you make the changes? How can you change the behavior, the same behavior as if happened here from this place to a remote place? And in context of quantum communication, entanglement could in effect teleport some information from one qubit to its entangled other half without the need for a physical channel bridging the two during the transmission. The very concept of teleportation entails by definition the lack of a physical network bridging between communicating devices. But it reminds that entanglement needs to be created in the first place and then maintained. To carry out QKD using entanglement, it is necessary to build the appropriate infrastructure to first create pairs of entangled qubits and then distribute them between a sender and a receiver. This creates the teleportation channel over which cryptographic keys can be exchanged. Specifically, once the entangled qubits have been generated, you have to send one half of the pair to the receiver of the key. Entangled qubit can travel through networks of optical fiber, for example, but those are unable to maintain entanglement for a short distance, about 50 miles, 60 miles. Qubits can also be entangled over large distances via satellite, but covering the planet with our space quantum devices is expensive. These are still huge engineering challenges. Therefore, building large-scale teleportation networks that effectively could link up qubits across the world. Once the entanglement network is in place, the magic can start. linked qubits won't need to run through any form of physical infrastructure anymore to deliver their message. This is something amazing in a quantum internet, and this is possible. During transmission, therefore, the quantum key would virtually be invisible to the third parties, impossible to intercept, and reliably teleported from one endpoint to the next. The idea will resonate well with industries that deal with sensitive data, such as banking, health services, aircraft communications, military operations, and defense, security, this kind of stuff. It's likely that governments sitting on top secret information will also be the early adopters of this technology. Why bother with entanglement, you may ask? After all, researchers could simply find ways to improve the usual form of QKD. Quantum repeaters, for example, could go a long way in increasing communication distance in fiber optic cables without having to go so far as to entangle qubits. When I was talking about repeaters, I remember my memories go back to about 29, 30 years. I was one of the early stage testers of classical repeaters, the Ethernet classical repeaters, in APCOM lab in India, and where we have to send the signals beyond 185 meters, which was a limitation of an Ethernet network, and it was successfully done. And this is exactly what is happening now in the quantum internet. I'm sure that the replication of classical network success will happen in quantum network also, though it may take a little bit of time. This is without accounting for the immense potential that entanglement could have for other applications. QKD is most frequently discussed example of what the quantum internet could achieve because it is the most accessible application of the technology, but security is far from being the only field that is causing excitement among researchers. The entanglement network used for QKD could also be used, for example, to provide a reliable way to build up quantum clusters made of entangled qubits located in different quantum devices. By connecting many smaller quantum devices together, therefore, quantum internet could start solving the problems that are currently impossible to achieve in a single quantum computer. This includes expediting the exchange of vast amounts of data and carrying out large-scale sensing experiments in astronomy, materials discovery, and life sciences. For this reason, scientists are convinced that we could reap the benefits of the quantum internet before tech giants achieve the quantum supremacy. The moment when a single quantum computer will solve a problem that is intractable for a classical computer. Linking devices together via quantum entanglement could result in clusters worth several thousands of qubits. For many scientists, creating such computing strength is in fact the ultimate goal for the quantum internet project. But in fact, quantum computing is different and quantum internet is different, and we do not need millions of qubits for quantum internet. We just need a couple of qubits to ensure the communication happens in quantum internet fantastically, providing multiple applications which we don't have a solution now. So for the foreseeable future, the quantum internet could not be used to exchange data in the way that we currently do in classical networks or classical internet. A lot of quantum communication research today is dedicated to finding out how to best encode, compress, and transmit information thanks to quantum states. Quantum states, of course, are known for their extraordinary densities. Scientists are confident that one node could teleport a great deal of data. US is doing great. And Netherlands, I could see QTech at Netherlands is doing great, and US is doing great, and some of the best educators on quantum internet, I could say Stephanie Wagner, Professor Stephanie Wagner from QTech, TU Delft, Netherlands, and Henry Ewen, Professor Henry Ewen from Columbia University, are contributing a lot by teaching these things to the students community, researchers, postgraduates, the PhD students, and of course to the industry people as well. And networkQ is also trying to contribute a bit from our side to the quantum internet learning, and of course we are working on the network simulations, quantum network simulations, quantum network research, In terms of quantum network research, we are presently working on a research paper, a concept paper, and I'm driving from the classical side to quantum, and Miss Nityashree Srivatsan, who's a young quantum researcher, is contributing from the quantum side, and there are a couple of more professors who are joining this research paper, and which is expected to be published soon. And I'm sure that also is going to help the quantum internet community across the world. So that's something which we have it in mind. And yes, in the upcoming series, we will be discussing about specific things of quantum internet, and yeah, hope it will be useful. Let it be interactive. You can communicate to me. The Twitter, the LinkedIn, and the email addresses are given here on the screen below. So yeah, let's work on the most exciting thing, the quantum internet. Bye bye for now.